SwayamPrabha. Digital India. Educated India.
I welcome you all to this lecture of flow through porous media. We were discussing about this immiscible flow, and we have talked about this concept of saturation and capillary pressure, and we are going to build on this further and see what insight we can draw from these theories. Now, this capillary pressure we had talked about, is basically inversely proportional to pore radius. This we already have seen, that P c is inversely proportional to 1 by R m, which is the mean radius of curvature, which is basically the mean radius of curvature as far as the that meniscus is concerned, and then that is related to the radius of the capillary at that point. And if it is a cylindrical capillary, obviously that is same as the radius of that capillary, or radius of, if it is a cylindrical pore, it is the radius of the pore that matters. So, capillary pressure is inversely proportional to pore radius. So, what that means is that if there is a wetting phase inside the pore and non-wetting phase pressure is gradually increased in the system. So, I have a system of pores, several pores, and let us say to begin with they are all filled with wetting phase, and then non-wetting phase pressure is increased gradually into this in the system. So, then as the pressure is increased, there will be penetration into some more smaller size pores. That means, we have already seen that the penetration will take place in the largest pore. So, let us say I think of a porous medium having a pore size distribution. That means, we are having a pore size distribution. Let us say we have a pore size distribution with the mean is about 1 micrometer, and the y axis. So, this x axis is the radius of the pore and and y axis is fraction of total pores, total number of pores with given radius. So, that means I am talking, when I am talking about this radius, this is the corresponding fraction of total pores. That means, if there are 100 pores and if this number shows 45, then I would say that this particular radius, which is maybe 0.5 micron, there would be 45% of the pores are having 0.5 micron. So, we can have a pore size distribution like this. So, naturally the pores that are larger, I mean since P c is inversely proportional to R m. So, that means, when we are talking about larger pores, that means where the R m is large, then the capillary pressure would be small. So, that would be easier, that would be the first place. I mean, as I am increasing the pressure from the water, from atmospheric pressure, as I am increasing the pressure, the first we will cross that pressure, because that is a low pressure. R m is higher, that means capillary pressure is lower. So, this is a lower threshold, and this lower threshold will be crossed first. So, lower threshold of capillary pressure is given by larger pores. So, that is why as the pressure is increased, there will be penetration, and this penetration into the first would be the largest pores will be penetrated, and then gradually as more and more pressure, as pressure is increased more and more, there would be some more smaller size pores, there would be penetration of non-wetting phase into some more smaller size pores. So, essentially what we see here is that increase in non-wetting phase saturation. So, what does this penetration of non-wetting phase into the pore means? Penetration of non-wetting phase into the pore means the non-wetting phase saturation is increasing into the pore. That is what the definition of saturation. So, what that means is increase in non-wetting phase saturation, or in other words decrease in wetting phase saturation, these are just reverse things. So, that will happen at higher capillary pressure. So, that means as the capillary pressure is increased, the non-wetting phase saturation will start to increase. And as the capillary, I mean by capillary pressure means I mean to say the pressure of the system. As the pressure of the system is increased, why you are calling it pressure of the system? We thought this as an idealized situation where all the pores are filled with wetting phase, that means water, let us say, and then outside I have dipped this entire porous medium into a beaker full of non-wetting phase, which is let us say oil, and then gradually I am increasing the oil phase pressure and obviously leaving some pathway for water to leave the system. So, if we get into this hypothetical situation, then I would expect that as pressure is increased more and more, then more smaller and smaller pores will be penetrated by oil, and what that means is more and more the oil saturation, that is non-wetting phase saturation, will increase. So, the pressure outside that we are originally, the pressure inside the porous medium was originally the porous medium contained water only at atmospheric pressure. Nothing happened outside oil, inside water, they will coexist. But now, if we increase the pressure of the oil, I expect some of the water will be moving out of the core, and in that place some of the oil will be getting in, and that differential pressure, that we are referring as capillary pressure. So, now this capillary pressure, if somebody plots with saturation, then this would appear something like this. See, mind it, here this x axis is wetting phase saturation, not non-wetting phase saturation. So, as non-wetting phase saturation increases, that means more and more oil get into the system, and that will happen only at a much higher pressure. So, that is why as SW decreases, that means wetting phase saturation decreases in this direction. So, in this direction wetting phase saturation decreases, non-wetting phase saturation increases, and that is reflected here, capillary pressure also increases. In this direction non-wetting phase saturation decreases, that means now we have less oil. So, now capillary pressure also decreases. Now, there are two limits to it, and these are the two limits we have put here. Though SW starts from 0 here and possibly go all the way to SW could be 1, right. So, 1 is the limit, it is basically a limit between 0 to 1, right, because SW 0.4 means S NW, that means S wetting phase 0.4 means S non-wetting phase would be 1 minus 0.4, that means 0.6. Sum of S wetting plus S non-wetting has to be equal to 1. So, now we are plotting with S wetting. So, S wetting, the minimum can be 0 theoretically and maximum can be 1 theoretically. But there is one small issue, which is the definition of something called irreducible saturation and residual saturation. Irreducible saturation, which is referred as SWI, which is given here, this is the irreducible saturation. What irreducible saturation means is the lowest wetting phase saturation, which is independent of further increase of externally measured capillary pressure. That means, if we continue to increase the capillary pressure, we will see that this will become a straight line like this, but saturation is not decreasing any further. What does this mean? This means that I have a porous medium filled with water. Okay. So, what was the saturation at that time? SW is equal to 100% water saturation, single phase present in the system. Now, we are introducing non-wetting phase, we are calling it oil, and this oil is being pushed into the system, and I am increasing the injection side pressure. and oil is going into all the pores, first the larger pores, then as I increase the pressure into smaller pores and pushing the water out from the system. But whatever pressure you impose, there would be some water will always remain in the system. Oil can never push this out from the system, or non-wetting phase can never push this out. This is a property of a random porous structure. That means, this is I mean, one can think of this as the, let us say these are the pores, this is a pore, and let us say water, if it is wetting phase or any wetting phase tends to flow like this, through this way. Wetting phase, because wetting phase prefers to stay near the wall, there is an attraction of wetting phase with the wall, because they go together. On the other hand, when it comes to the non-wetting phase is sitting here at the center of the pore as a blob, and when you inject non-wetting phase, so non-wetting phase will create a pathway through the center of the pore. But if you expect this non-wetting phase to go all the way and displace the wetting phase from everywhere, 100% displacement, that does not happen. So, that means there would be, as you increase the pressure, maybe this part would be filled, this is probably grow, but there would be some remnants of water always remain there, and that is referred as the irreducible saturation. On the other hand, now if you look at the other side of it, that means when these, now when you go back and then you start pushing water through the system, try to push the oil out from all the pore. At that time, this will shrink, this oil will shrink, this oil will shrink means there would be more water traveling here like this, but there may be a small speck of oil sitting at the center, which may not be, one may not be able to displace. That is called residual non-wetting phase saturation or residual saturation. So, I have two limits here. Here it is not going all the way to 1, but before that there is a, so this is given as 1 minus S. So, if you call this residual saturation as S non-wetting residual, if I write this S, this, if this is SWI and 1 minus SNWR, SNWR non-wetting residual, if I write, then you can see here the residual saturation becomes the lowest non-wetting phase saturation arising from entrapment. So, you call this the entrapment. This non-wetting phase is entrapped by the wetting phase. So, entrapment, when the externally measured capillary pressure is decreased from high value to 0. So, that means externally measured capillary pressure is decreased from high value to 0. That means there is no capillary pressure, you are not injecting any oil to the system, oil from outside, it is all water. So, there is no capillary pressure, no oil pressure externally imposed. So, that is 0. So, at that time, so at this other end, there would still be some lowest non-wetting phase saturation existing. So, that lowest non-wetting phase saturation is SNWR, and this irreducible saturation is, already we said it is SWI. So, since we are drawing it on SW scale, so that is why I am writing it as the limit for SW is 1 minus SNWR, because the sum of SW and SNW, basically SW plus SNW, that has to be equal to 1. So, here in SW, since the axis is for SW, so I have to write it as 1 minus SNWR. So, this is the residual saturation, and there is this imbibition curve which says that the relationship characteristics of the displacement of non-wetting phase from irreducible saturation to the residual saturation. So, displacement of non-wetting phase from irreducible saturation to the residual saturation. Irreducible saturation is this SWI to this one. So, this is known as imbibition, because this here in this case the water saturation is increasing. That means, it is water is simply imbibed into the porous framework, whereas the drainage curve, I mean, this is exactly what we defined in a layman's term what is drainage and imbibition. So, in rigorous terms, it is the drainage curve is the relationship characteristics of the displacement of wetting phase from residual saturation to irreducible saturation. That means, from this side to that side. Generally, now here in this context, one may see that when this is gone backward, it may take a shape like this. So, this curve is known as drainage and this curve is known as imbibition. So, imbibition means the water saturation is increasing, oil is thrown out of the pores, or wetting phase saturation is increasing, non-wetting phase is thrown out of the pore. Whereas, drainage means now you are increasing the capillary pressure. You can see you can increasing the capillary pressure and the non-wetting phase is gradually getting into the pore, first the larger pores and then the gradually into smaller pores at much higher pressure. So, this is going backward now. Okay. So, now only point to be noted here is that these two curves are different, they are not following the same pathway. This is when it is drainage, it is going this way, when it is imbibition, it is coming this way. So, one must look at, I mean, why it happens, but more or less this, I mean, it's not completely unexpected, because the way the pore was filled, you can see when oil entered through larger one, when water entered through the other side. So, naturally the pathways are different, I mean, the same pore is getting filled, but through different pathways. So, you can never expect that they would follow exactly the same line. Anyway, so with this, now let us see the way to determine capillary pressure. Now, we will get to that capillary pressure hysteresis. We are referring to capillary pressure hysteresis, that we will go to in later, but let us first talk about what is this capillary pressure, how capillary pressure is determined. There are two ways one can do it. One is known as porous diaphragm device. Porous diaphragm device, it works something like this, that they have on one in porous diaphragm device, let us say this is the porous medium, this is filled with the wetting phase. This porous medium is first of all placed in a ultrafine fritted glass disc. So, this is ultrafine fritted glass disc, this is placed here. Then whatever is being collected, that is being first of all, this is completely filled with water, and then there is a graduated scale is there, and then there is a small oil plug is present. So, that there is no evaporation can happen through this, because if there is evaporation, then there could be this change in the height, because so that to avoid that they put a small oil blob here, and then so this is filled with water. If it is a reservoir, if this porous medium is taken from a subsurface reservoir, generally instead of water they prefer to use brine. The reason I already mentioned. So, this brine is basically 1% NaCl. Instead of pure water, they put water with small amount of NaCl. So that this porous medium, that there is not any soiling or any other clay material will not come out of the porous medium. Okay, so, to avoid that, and then this is placed inside a chamber, and this chamber is filled with oil, and then there is a, this chamber is filled with oil, then there is a top and there is a spring by which this porous medium is held in place, and from here there is a, from the top there is a nitrogen connection, and one can change the pressure nitrogen by putting. So, this is all filled with oil, this is oil. Originally there was brine or water filled, brine or water, it was inside this porous medium. So, this is porous medium, this is the porous block, and then oil pressure is gradually increased by application of nitrogen pressure on top here. So, that pressure will, so gradually water will come out. Now, this particular ultrafine treated glass disc will not allow oil to flow out, only it will allow water to flow out or brine to flow out. So, amount of, so oil goes into the porous medium and the brine comes out of it, and whatever brine comes out, so this here the level rises on the right hand side, and that rise is measured by the scale that is provided. So, let us just try to articulate what is mentioned here. Sample saturated with wetting phase, this is the porous medium porous sample saturated with wetting phase is placed in a chamber with ultrafine fritted glass disc to prevent passage of oil. The glass disc permits the passage of wetting phase. So, when oil gets into this pore, then the water comes out, and that water can be drained through this ultrafine fritted glass disc. As the pressure on the oil is increased, the wetting phase is displaced from increasing smaller pores of the sample. That is, as the pressure on the oil is increased, the wetting phase is displaced. Wetting phase is water or brine that is displaced from increasing smaller pores of the sample. So, first when the pressure is increased, first the larger pores will be penetrated by oil, but as the pressure is increased further, more increasingly the smaller pores will also be penetrated and the water will come out of those, and that would be collected. Now, volume of wetting phase forced out of the sample by non-wetting fluid is determined in the graduated portion of the tube, that means here. So, here as this oil plug, as it is rising, so from here one can see how much is the water level rising, and that water must have come out from this porous medium. So, this is how this porous diaphragm device works. Of course, the whole process it depends on the effectiveness of this ultrafine fritted glass. It should allow water freely, but it should plug oil completely. So, instead of relying on this, there is an alternative way that was suggested, and that is something like this: capillary pressure determination by centrifuge method. So, in this case, a small uniform plug is initially saturated with a wetting fluid and is held in a cup containing non-wetting fluid, and this cup is rotated at a series of increasingly angular velocities, increasing velocities basically. So, the cup, this is the cup, the oil is the plug, this uniform porous plug, that plug is placed inside the cup, and this core contains, this porous medium contains water, and outside it is non-wetting phase. That means, inside the cup, outside the porous plug is all oil. So, now this cup is rotated at a series of angular velocities. So, that means, this cup is placed in a centrifuge and this cup is rotated, and because of this rotation and at some angular velocity, and then next at some other, and then some other at gradually increasing angular velocities, and the quantity of wetting fluid that is removed at each speed of rotation. So, at one speed of rotation, So, basically the omega, which is the speed of rotation, is increased step by step. So, at one step whatever omega value is there, that whatever omega value is there. So, against that there is some collection quantity of waiting fluid. So, that is collected. Then the pressure at the inner radius of rotation, that is at the inlet face of the sample, is PC1, which is the capillary pressure. So, here you can see that the quantity of waiting fluid that is collected, that is noted there. Now, one can see that the pressure at this face, pressure at this face and pressure at this face, what is the difference between these two pressures? That is the pressure at the inner radius of rotation, that is at the inlet face here of the sample, is PC1, where PC1 is half delta rho omega square. Delta rho is the density difference between oil and water. Now, inside it is water, outside it is oil. Oil density is lower, okay, typically say 80% of the density of water. So, that delta rho is there, omega square, that is the rotational velocity, and R2 square minus R1 square, R2 square and R1 square. So, this is R1 and this is R2. So, these are the two radii. So, PC1 is defined as this one, and the capillary pressure at the other end is basically the pressure of water and oil at the other end is basically 0. So, on one side this is the pressure. So, here omega is angular rate of rotation and R2 is the outer radius of rotation, where pressure has same value in both phases. So, pressure in water, because it is basically it is open. So, now waiting fluid has greater density than non-waiting fluid. So, as the omega is increased, so waiting fluid will tend to go out from the so you have, it will be collected in the cup. The cup is already there, but waiting phase will be coming out of the plug or out of the porous plug, and in that place the non-waiting phase will enter. And what is that gradient? What is the pressure difference? That is half delta rho omega square R2 square minus R1 square. So, waiting fluid has greater density. So, delta rho would be positive, and then than non-waiting fluid. Average saturation is obtained from the volume of displaced waiting phase. So, for a particular omega, this is rotated, this is the capillary pressure, and corresponding saturation is measured from the displaced waiting phase. So, if I look at the earlier case, we had the diaphragm device. There, what did we measure? We measured at various pressures, we measured the pressure versus saturation. So, I set the pressure at some point, I find that this much of water level has gone up. So, from there I can find out what is the change in saturation in this porous plug. So, gradually I can draw I can draw the capillary pressure in that case, capillary pressure as a function of saturation, just by the same way, and we can go reverse and we can draw the other side. So, this is how we can do this here, and at the same in a similar way, if somebody follows the centrifuge method, in that case also this becomes the capillary pressure, and the corresponding saturation would be obtained from the volume of displaced waiting phase that has to be measured. So, either of these two methods can be used to find out capillary pressure versus saturation curve, okay, with increasing, I mean with imbibition as well as in the drainage part of it. So, this is all I have as far as this particular lecture is concerned. We will continue, our aim would be to use these concepts into two phase flow, because next what we will do is we will talk about the capillary pressure hysteresis, and then we will try to get to the Darcy's law, the flow equation, how that will be modified if we have two phases present, two phases are together and flowing. So, keeping these capillary pressure and keeping these concepts of saturation, surface tension, contact angle in mind. So, that is where we are heading to. So, this is all I have as far as this particular module is concerned. Thank you very much.